Hello. Hi. Good evening, Anurag. We'll wait for another 2-3 minutes so that others can also join and then we'll start the discussion session.
Hello, good evening.
Hello. Good evening.
Good evening, madam.
Yeah, good evening, sir. So we'll start the discussion session after 2 minutes. Let's wait for the others also to join.
Today we are discussing this assignment 9
Yes, assignment 9.
and
Week
week 9.
Assignment 9 as in the week nine's content. So the discussions are mainly about last year's assignments. This year's assignments we won't be discussing.
Okay, okay. Because just 2 days before we have submitted the assignment 8, so we got very less time to go through this 9 all chapters. But still
Okay.
no problem there. That is in front of me. That is all the lecture material. So we
Okay.
can go through it. Yes.
Okay. So I think the deadline to submit this assignment is tomorrow, right?
Tomorrow, yes.
Yes. Yeah, I mean, uh, without going through the lecture, it might be a bit difficult because we'll mainly look into the application side over here. But I think
Hmm. No,
we'll
that is possible. No, no
yeah,
problem.
it is
All.
possible only, but yeah, we'll discuss most of the concepts here once more if time permits. We'll look into that.
Thank you. Because now for me it is almost 27 years from the engineering. So solving again the this mathematical question.
Correct. Yes. I'm sharing my screen. Okay. I hope my screen's visible and I'm audible. Everything okay? If yes, we can start.
Yes, okay.
Yeah, okay. Thank you for the confirmation. Good evening once again, everybody, and welcome to today's tutorial on urban utilities planning, water supply, sanitation, and drainage. As we might have gone through the lectures, today we will be discussing about module 9. That is, it has like how do we design runoff estimations and sewerage network design. So these are the three topics which we learned. So we'll try to solve certain assignment questions, mainly the questions which were given in previous years' assignments. We'll try to solve for these contents. So before we begin, as usual, this is the rules which we normally follow. I think most of you are already familiar with it. I'll just take 1 minute to go through that. So we'll discuss. So I have around 16 questions planned for today. Let's see how much we can complete. It's not necessary we need to go through everything. So yeah, so after each question, we'll have a small break where we can, small 1 minute window where we can discuss about that particular question, any doubts, and after the whole session, last 5 to 10 minutes, any other doubts if you have regarding module 9, we can discuss that also. So yeah, let's get started. So question 1 is on self-cleansing velocity. So self-cleansing velocity depends on which of the following factors? Let's go by how it's just a few of us, right? So let's go by one person attempting each question if that's okay with everybody. So may I request somebody to volunteer and take this question up?
Option D.
Anurag says it's option D. Okay, self-cleansing velocity depends on particle size, specific gravity of the particle, conduit shape, and depth of flow. Okay. So, firstly, Anurag, what is self-cleansing velocity? Or anybody, what is self-cleansing velocity?
Madam, good evening. Self-cleansing velocity is the minimum velocity required to automatically clean the sewage. It has to take out all the silt, dirt, or whatever the particles are coming. That is called as a self-cleansing velocity.
Exactly. It is to automatically clean. So basically, we say that it is a minimum velocity. That is so that this much minimum velocity should be there so that no deposition happens within that entire pipe. Because if it's going very slow, then like certain sediments or highly dense particles can get settled inside the pipe. So that's why we always design the flow in the sewage to be greater than the minimum velocity of the self-cleansing velocity. So yes, so there are certain factors which influences it. So Anurag has said that it is option D. So let's look at what we learned. Yes, so in self-cleansing velocity, yes, it basically depends upon the particle size and specific gravity. So this is understandable. Like whatever material is going, so if the particle size is larger, then we would need a greater self-cleansing velocity so that we need to carry this material also forward. And specific gravity also, like for water, it has a specific gravity of 1, grit has 2.4. So if it's sand or any other material, we need to consider that also. And obviously conduit shape and depth of flow also. By conduit shape, because based on the shape of the conduit also, the flow depends, velocity depends, simple, and depth of flow. So this was a very simple question. Yeah, so Anurag answered it rightly also. So let's proceed on to the next question. So this is two questions are combined together for one data is given for that question. So the data says that the sewer is laid at a 1 in 600 slope and the diameter of sewer is 150 centimeters. Assume n to be 0.015 in Manning's formula and the sewer is running half full. So question 2 asks us to find what is the velocity of the flow in the sewer. So there are no options to this. We need to enter the right answer. So yes,
We can use this formula 1 by n d raised to 2 by 3 s raised to half. Okay,
exactly.
and here this radius shall be taken as the same because it is running half. If it is running full, it has to be 1 by 4. Is it correct?
Uh, no, radius, no, we are take, you're talking about R in the formula,
Yes,
right? That is
yes,
V
yes,
is
sir.
equal to 1 by N into R
Hmm.
raised to 2 by 3 S. Okay, you said S raised to 1 by 2. So in this,
Hmm.
you're saying you don't have to make any change. That's it, yeah. So in
Yes,
this, you're
yes.
saying you don't have to make any changes because it is running
Half.
half. No. So if it is running, so what is R? Like, let's discuss what
H
is
is R is the radius, na, madam.
R is not
Hydraulic
R is not just the radius, it is the hydraulic
hydraulic
radius.
mean depth.
Yeah, hydraulic radius or hydraulic mean, like both we are calling it. So that is not equal to the actual radius of the pipe, right? It basically is area divided by wetted perimeter.
Yes.
This is how we are getting this. So
Yeah,
that yeah, so that so if we and here in this particular case, the pipe is running only half full, which means our wetted perimeter will not be the actual perimeter, but it will be half.
half.
So R will change, like compared to taking the normal, like a fully running pipe and half running pipe, it will change. So it'll be, I wouldn't say it's exactly R, but let's see what that comes. Like we'll
Okay.
discuss that further. So yeah, so as we were here, uh, your R is equal to wetted area by wetted perimeter. I'm just writing it A by P. So A pi d square by 4, and P will be, instead of pi d, now it will be pi d by 2, right?
Hmm. Yes, correct.
So this we can simplify it, and this will eventually be d by 2.
Hmm.
When we cancel out pi, 1d will go, this will be 2, so it is d by 2, right? So yeah, so now if it was not like this, like if it was running full, then it's d by 4, but now
4
that it is running
d by 2.
full, it is d by 2. So that is the major change which is happening over here in this formula. And let to summarize, so this is the Manning's formula that we are using over here, Manning's formula. We have learned about certain other formulas also, like in the previous lectures. Can somebody just discuss, like give the names for that? Yeah, so we have learned certain. I'm not giving it. I think you can go back and see because that will be important later, like certain other formulas. But then the reason why we use Manning's formula here is that it is because the pipe is half full, or like the pipe is not running fully full. The other formulas which we used mainly considers the pipe to be fully full, like full flowing pipe is what we use. So in the software also, which we discussed in our lectures, we're telling that by default we usually put the Manning's formula, but then if the pipe is running full, we can even change it to other formulas also, right?
Shield formula.
Huh?
Shield formula or which one?
No, no, not shield. It's in the previous
No.
lectures. We have William Hazen's formula ways back. Like there are certain formulas for that. So it was mainly we discussed it in water supply, that lecture where we did some numericals also based on that. Right. So, yeah. So let's solve this question now. Now that we know what R is, so I'm just writing the formula once again: 1 by n m raised to 2 by 3. Okay, R raised to, since we discussed R raised to 2 by 3, R and S raised to 1 by 2. So here now we found what is R, and what was our yeah, so R, we did not find the value. So let's just go back and find from the question. So the diameter of the sewer is 150 centimeters, so 1.5 meters. So
Yeah,
yeah, so let's
0.75.
yeah, so 0.75 will be our R over here. So I'm just writing it here, 0.75. And now we can solve this. So N also, let's see. So N is given, like from Manning's formula, this is N which is given, which is basically the coefficient that we're taking. So let's just put everything in place, 0.015. And okay, this is the slope also, like S stands for the slope, or the gradient which is there,
Hmm.
slope of the gradient. So let's just put everything in place,
So 1 by
0.05
600.
raised to 2 by 3, which is yeah, 1 is to 600 raised to 1 by 2. Yeah, can we quickly
It,
solve this?
it is coming 0.51. 0.51. Hmm.
0.51. No, that's not the correct answer.
So
Let's,
let me try again.
yeah, yeah. Let's try again. Okay, so ML says it's 2025. ML, okay, 2.25.
2.224.
Okay, yeah, correct.
2.24.
Yeah, so yes, correct. 2.2466. This is the answer that we will be getting. So now we can round it off and write it as 2.25. That's also correct. So, do our any of our, okay, we don't have an option. So, yeah, so they have asked us to answer, to round it off to the nearest two decimal places. So, 2.25 is the answer for this particular one, right? Okay. So, let's proceed on. The second part of this question is, what is the discharge flowing through the sewer, and enter the answer. So now we basically found what is the velocity. So we know that in case we get the velocity, then we can easily find the total volume. Discharge flowing means they're basically asking what is the volume which is flowing. So how do we go about this? V is equal to,
QA,
yeah, V is equal to Q.
Q by A. Huh.
Yeah, so V is equal to Q by A. So here our Q will be equal to VA, but now
VA.
there is a change over here. Can we directly apply this formula?
Area will change, madam. Area is half running. Huh.
Exactly. Area will change. So it will be totally half of VA. Like that will be the formula over here because the pipe is only half full. So now we can easily solve this. So I'm just taking 1 by 2 outside, and area again pi d squared by 4 into V. So this is 1 by 2 into, okay, pi D, which yeah, for D
1.5.
was 0.75 whole
No,
square.
no, D is, madam, D is point 1.5, not D.
Yeah, sorry. Yeah, D is 1.5. Yes, sorry, I made a mistake. Yeah, D is 1.5, the whole square, into 2.25. I'm taking the rounded off value itself. Yeah, so let's solve this now. Okay, there's one answer in the chat box.
2, 2 is answer.
Yeah, so that's completely when we round off. So 1.987 is what we are getting. So if you look at the question, it's mentioned rounded off to two decimal places. So we can only round it off to 1.99 meter cube per second. Two, absolutely, two is the answer. But then when such questions are asked, where we are asked to enter it up to correct two decimal places, we will have to enter it this way itself, 1.99. Okay. So, shall we proceed?
Yes, yes.
Yeah. So this is also numerical. It is very similar to what we did right now. So let's try to do it uh, alone. So consider the following data: circular sewer diameter of 50 centimeter, slope 1 is to 220, and n is also given the same 0.015. And question 4 asks, what will be the velocity and discharge of flow in meter per second and meter cube per second respectively? So let's go with the same method which we did before. And you can do it independently. You can attempt it. I'm just writing down the steps. So in case you have any doubt, you can look on also. I would suggest you to do it independently. So just a confirmation, M here, sorry, R here, I'm used to M, that's, yeah. So R here is D by 4 because the first part is pipe is flowing full. So that's the only change which is happening over here.
Answer will come 1.42.
Correct. 1.4,
415.
1.4. Okay, let's just see. So this our calculation comes up to this, right?
Hmm.
Yeah. So I don't know where it's going wrong. So this one will be 0.25, and this one will be 0.0674. So when we multiply everything, can you just check that once more?
Yes,
Yeah,
yes.
so MLS put the answer. It is 1.12336 is what we will be getting. So we are again rounding it off to two decimal places. Though, okay, basically we need to see from the options also what is there. So it's 1.124. That is velocity what we are getting. Okay, shall I proceed to the next part?
But my answer is coming 1.4 only, madam. Maybe.
1 point, no, but if you do this calculation, that is
Oh,
0.25 into 0.00764 divided by 0.15, it will come up to
okay,
1.1233
okay.
something, right?
Okay.
You can do that, like no problem. You can r is to power 2 by 3. Yes, r is to the power 2 by 3. And ML had put this in the chat box. Yes. Did I write it wrong? Yeah, it is 2 by 3. Oh, okay, here. Yeah. It is 2 by 3. Okay, so this question is not over here. Like, so we just found the discharge flow. Now we need to find what is the volumetric flow also. So that the same way how we did the previous one. Let's go Q is equal to AV. Now here it is easy. Pi V square by 4 into V, which is equal to pi into, now this is, I'm just doing. In the solution part, yes, I understood. Thanks, ML. Yeah. So I'm waiting for the final answer over here. Okay, ML says it's 0.221. Yeah, so we can take it as 0.22 meter cube per second. Right. So yes, so coming back, it is there in option A. Okay, I'll wait for 2 minutes. Any doubts in this question? And also if uh, Shripad, if you've not got the answer rightly, like we can discuss over it. Let's see what is going off.
Let us continue, madam, because I have taken the whatever the velocity I have calculated from 1.4, so that will be different.
Okay, fine. Yeah.
Okay.
So yeah, you can check this, and in case something if you're feeling off, then you can put it in the
Hmm.
discussion forum also later if you're facing any difficulties. Then we can take that up later also, or by the end of the class also if you are able to do it. Yeah, we can. But it's the same method, so there is nothing.
Yes.
Yes. Okay. So if that's the case, proceeding further to the next question. Question 5, which is what would be the velocity and discharge when the same is flowing at zero point 0.3 meter of its depth full? So how will we do this question? How do we approach this?
Actually, one table is there from where we can get the values of, for 1.3 full depth,
Yes.
Exactly.
and similar process can be followed.
Exactly.
It's,
So yeah, so the crude method would be to recalculate the whole thing by calculating what is the hydraulic radius, what is the hydraulic mean or hydraulic radius based on this when it's only zero point 0.3 depth. But that is very time consuming. So once we have the data for full flowing pipe, like how it would be, we can obviously use the already existing relationships, the proportionality relationships, and find. So this is the table. Right, yeah. So this is the table that Supriya was talking about. So we have the proportionate hydraulic elements, so based on proportionate depth, how it is. So it's basically derived, like it's a graph which comes like that. So this is the table which we will be following. So over here we've been given it is zero point 0.3, like when the proportional depth. So proportional depth is given to be zero point 0.3. So this is the data which we will be using over here, right? So let's see if that is the case. Let's take both the values. That is, what would be V? So we need, so if you look, it's given as V by V and Q by Q. So V by V and Q by Q is what we will be needing. So these are the two values which we will be taking. So let's solve the first part, which is V by V is equal to 0.776. So which means the actual velocity which we require, which will be there in the 0.3 meter depth, would be 0.776 into our velocity which we found for pipe flowing full. So this is, I forgot to explain. So this is the case for full. Capital V is for the case for full, and small v is what we are interested in, or the value that we need to find out. So that into our previous question, 1.124. So 124, yeah. So that will give us the value. So if you observe, if you get the first part, like the velocity part, wrong, then the whole thing might be chained and that might go wrong. So we need to be a bit cautious about the first part. So yes, so this one, it works up to 0.07. Okay, ML, you got a different answer. Wait one sec, let me check my answer. Yeah, sorry. My mistake. It is 0.65. Yeah. Okay. So, okay. No. Actually, yeah, if you, sorry. The thing is, we need to take the whole value. I just took 0.77. We need to take 0.776 itself because that is the value which is given over there. So, yeah, so ML, you need to make that change over there. It is 0.776 itself. You need to take that. So, that works up to 0.776 into 1.124. It is 0.872, it would be meter per second. Yeah, correct. So this was my mistake. I forgot to write the 7 over here, but we need to take the whole value because the value is given, right? So now the second part will be Q by Q is equal to, let's go back to the table. It is 0.1956. So 0.1956. Q is equal to 0.1956 into capital Q, which we found it as 0.22. So how much does that come up to? Correct. 0.043 meter cube per second. Right. So let's go back to the question. So that is there in option B. So this is the correct answer. Right. So this set is over. We have one more question, like three questions based on this data. We have one more question. Uh, can I proceed further, or do you want me to like halt for 2 minutes so that you want to catch up? Like, Shripad sir, like, can I proceed further?
Yes, it is okay.
Okay. Yeah, fine. Yeah. So I'm proceeding further. So the next portion is, it's very similar to the previous one. Now this one is asking, what would it be when the pipe is flowing at zero point 0.7 of its full depth? So let's do it the same way how we did the previous one. Yeah, so this one I am not going to do. I would request you to try it and then just give me the final answer. So the two values would be V by V would be 1.120 and Q by Q would be 0.7258. Okay, ML's got the answer. Fine, very good. ML says the next one is, yeah, correct. I'm just waiting for 1 more minute so that I can get the answers from others also. Correct. Anurag has also got it. Right. So this, let's see which is there in the options over here. So this basically works up to our, okay, 125 is there. This one, yeah. So it basically works up to option C, which is the most accurate answer. Like, yeah, we got 59, like 0.59. So 0.16. So this is the answer over here. Right. So shall I proceed further? Yeah, okay, I'm proceeding further. Yeah, so we are in question 7 right now. So question 7 is the different applications of SWMM include. So firstly, what is SWMM? Supriya, what is SWMM? Do you want to take this question up?
Yeah, I forgot about this. I attended the lecture, but not able to recall it.
Okay. So ML is typed stormwater management. So ML, do you want to take this question up? Not much. Okay, you can guess. It's okay. Okay, fine. So ML is right that it is storm water management model. So this is SWMM. So it's the software which we use to find stormwater. So why we use software again? Because it's very complex, the whole process that we're doing, like to manually sit and calculate for every node, like the network, the sewage, stormwater network can be very complex after when it comes to designing for a large city area or for in fact any area, like it can get very complex. So we use high softwares for that. Yeah. So, yes. The different yes, multiple answers can be correct for this. Yes. Okay. So, so here option A is asking the design and sizing of drainage system for flood control, the sizing of detention facilities for flood control, floodplain mapping of natural channel systems, and control strategies for minimizing combined sewer overflows. So let's go by everything. First one, is it important? Supriya, do you want to take? You were answering this, right?
No, but I can now.
Okay, yeah, fine.
Design and sizing of drainage systems can be a model for the stormwater drainage design, and size of detention facilities. Not sure about this. Floodplain mapping of natural, yes. Control strategies for minimizing, yes.
Okay, so you're saying basically A, B, and D. Sorry, A,
Yes.
C, and D, right? Okay, why not? Okay, obviously, design and sizing of drainage systems is important because so what we're doing with the software is basically stormwater management only. Stormwater management. There's nothing more. It's just that it is a software application. Like we are using a software to do that. So obviously, to design our drainage systems, it is important, and sizing of detention facilities of flood control, that is also important, and SWMM allows that also. Like we can design or see what are the different detention facilities and how do we size it, and based on that, how is our management model changing, how much pipelines required, all that we can calculate in this. And yes, floodplain mapping also we can do, and control strategies for minimizing combined sewer outflows, that also we can do. So let's just see. This is what we learned about SWMM model. So yeah, so all this design and sizing of drainage, sizing of detention facilities, floodplain mapping, control strategies. So all this are included. Right. So all the answers are correct. Yes, ML, you're right. All the answers are correct. You should have attempted it. Right. So let's proceed further. In question 8, the question asks, dash of a stormwater event may be defined as the average recurrence interval between events equal to or succeeding a specified magnitude.
It's a return period.
Return period, yes.
Okay. We kind of discussed this in the last discussion also, like what is return period, and we discussed this. So answer is right, it is return period. Let's go by the options and let's see what are the other options mean. Like what is design period?
Design period is based on
Life of that
for how
product,
much. Yes, yes, you can.
life of the system, madam.
Yeah, life.
Yes.
Okay, you can call it life. Yeah, basically life of this any system also. So here we are mainly talking about service or utility. So yeah, so we say it is the life of the utility that we are providing, or the whole service that we are designing for. How many years will it last? Usually, it's taken to be about 30 years for the entire capacity that we are building it for. What is hydrograph and time area histogram?
No idea.
Okay, so this is there in a lecture. So hydrograph is basically the it's a graph which shows the distribution of rainfall. Like in one word, we can say that it's a distribution of rainfall, and basically in the x-axis we have the duration of rainfall, like time usually, which is given in minutes, and on the y-axis we have the precipitation, that is how much rainfall is coming over time. So why this is important is because we have learned that in a catchment, previous class also we were discussing about time of concentration. So from different regions, if you're taking a point, the area of concentration or the region where we want to find how much, or basically it can be the catchment inlet or any point where we want to find how much of rainfall is coming. Sorry, went to a different slide. Yeah. So time of concentration is important. So from different regions, from different times, like it will take different time for water to reach that particular point. So that is why we are plotting this. That is at a point for different duration. That is from 0 minutes to 10 minutes to 20 minutes. How much of water is coming to that particular point? So it's a histogram because it will keep varying. That is, firstly, water, like in 10 minutes, water from this location comes in. 20 minutes, water from this location also adds in. So it can be there. Sometimes then after a certain duration, rainfall also drops. So rainfall is the intensity of rainfall is also reducing. So the overall this one in after 30 minutes, the water which is coming into this point can reduce. So it's a basic histogram that we are plotting. And time area histogram is again it's taken the time for surface flow to reach the overall catchment. So it's basically a continuous, like it's a cumulative graph. So this is not a cumulative graph. This is only for that particular point which is there. And for time area histogram, we look at so in the x-axis we have time, and on the y-axis we have area, and the overall catchment is divided into certain regions, like it's called isochrones. So from this isochrone, when will water reach over here? This isochrone, like from this area, when will water reach? So based on that, when if I'm taking the inlet as or the catchment mouth to be somewhere over here, the pipe mouth to be somewhere over here. Sorry. Uh, in each time, that is in the first 10 seconds, water from this point will reach over here. So we have for that particular area, we have certain value which is coming, and then the next point we have from the other areas it will also come. So it cumulatively adds up. Let's see that over here. It'll be much clear. So this is the hydrograph which we were discussing. So basically for each duration, how much is the precipitation which is coming, so which is the intensity of precipitation. So we see that at certain points it's increasing, so then certain points it's again decreasing. So that is the histogram. So we have all the details of how do we plot it and all. And yeah, so this is our time area curve, which we were talking about in the second one, time area method. So this is what I was trying to explain. So basically, if this is the catchment mouth, then firstly, we'll only have from this A1 area, that is in T1 time, water will initially flow. So that comes over here, that is the T1 times whatever. So intensity over there. So intensity again, we get it from our IDF curves, that is last class we discussed. So that's from where we get the intensity. So that intensity will be there. Then in the next one, water from this region will also come. That is, it after certain at time t2, water from this region will also come, and the intensity also at that time. What is the intensity? So previous intensity plus the next intensity will also be there. So yeah, so like that it adds up. So this is the cumulative time area curve which we are using. So I just explained it in a very high level, like in very simple or initial discussion only. For more detailed discussion, I would strongly suggest you see the lecture, because in the lecture, professor is explaining it very detailedly. So all the step-by-step methods by which this can be done is explained. So that will give more clarity. Yes. So yes, so this is, yeah, so we basically discussed all this in order to look at what this is. So yeah, the answer is correct. It is the return period which we are discussing over here. So yes, so let's go to the next question. It's again about return period. Return period selection of a storm depends upon which of the following factors. So again, multiple options are correct for this question also. So let's go one by one. So drainage area, like it depends on the importance of drainage area. Does it depend on drainage area, the return period?
Yes.
Yes, it depends upon the drainage area. And socio-economic conditions, does it depend?
Yeah, this is also right.
So that is also right. Uh, Again, why socio-economic conditions?
Yeah, because
No, mostly. So
Depending on the covering of the area, madam, that is impervious by the roads, buildings, or other
infrastructure,
facilities,
you can say.
exactly,
infrastructures.
exactly. So it depends upon the so when you're talking about area, it's just the physical radius or the area that we're considering. But when we give the socio-economic conditions only, it actually defines what is there over there. Or how much, when will it repeat? Like how much water will evaporate, how much will percolate, how much will be the surface runoff. So all that depends upon the overall socio-economic conditions or or what is existing over there. So as rightly said, yes, it depends upon the available area, what is there, everything. So yes, so that's why B is also right. Now constraints, funding and availability of space, will that depend?
This is already covered in socio-economic
It is
conditions.
covered, but yes, so that will also depend actually, like availability of space. So it is interlinked. So as a separate option, it is not required, as rightly said. But if it is given, then it is there. Like obviously, that is also one important factor. And the last one is design period of infrastructure. Will that depend?
Yes, that will depend.
Yes.
Okay, so there is a small twist over here. So design period of infrastructure, it's basically the infrastructure that, or the utility that we are designing. That's what is meant over here. So we said that design period for 30 years, 20 years, we usually design it. So the relationship is the other way around. That is basically the design period of the infrastructure is based on the return period. So return period is how much time it will repeat, or the recurrence which is happening, which doesn't, like, because your infrastructure is designed for 30 years, or if it's designed for 35 years, your return period will not change much. So it is not, that direct relationship does not actually exist. So the other infrastructure, socioeconomic conditions or other constraints mainly depend upon the surface level of what is happening there, so that you know the system or the overall pattern in which rain will fall and the evaporation happens, everything. But the overall infrastructure that we are designing for water supply, like I think it should have been mentioned that our water supply infrastructure or the sewerage infrastructure is what they are mainly talking about over here. So that doesn't affect the return period actually. So option A, B, and C are right, but the the relationship for design period of infrastructure is that design period depends upon the return period. Like I wouldn't say directly proportional. So design period, it has a relationship with the return period, but return period is not dependent on the design period. So here we have asked for selection of storm water like the return period for selection of stormwater. So that does not depend upon the design period, right? So yeah, so let's proceed further. So yeah, so this is the slide which we learned. So it only depends on the importance of drainage area, socio-economic conditions, and constraints, the funding availability which is there. So limitations in adoption of discount period can be overcome by provision of rainwater harvesting structures and rainwater detent to accommodate the excess runoff. So all that is covered. So this is what we have discussed before. So return period we don't have to consider it because there are other methods by which we can overcome. Fine. Let's proceed further. So, in question 9, it's a match the following. So, let's go one by one. What is inlet time? Like, which of the options will correctly represent inlet time? Is it the time required by stormwater in traveling from the uppermost inlet up to the point of concentration? Is it the maximum flow? Okay, is it first one?
No.
Okay. Second, is it the maximum flow while part of the upstream catchment is contributing?
No.
Okay. Time required by runoff. Supriya, why don't you answer this question? I mean, that'll be much easier.
I think the third one is for P third.
P is third. Okay. Time required by runoff from the most remote point of the catchment to the flow across the ground surface drains to the inlet of the sewer. Yeah, right. You're right. So this is 3. Next one, time of travel.
Time required by runoff from most remote points. It is 4 to reach the concentration to the point. Yeah, it is 4 time. Q4.
You have two things. You have time of travel and time of concentration. So which is which?
No, 1 second. Time of travel would be 1. It is uppermost inlet up to the point of concentration, and time of concentration is the 4th one.
Exactly. Okay. And what is partial area of it?
Maximum flow while part of upstream catchment is controlled.
Correct. Correct. So that I think corresponds to option A, right? Yeah. So yeah, so you're right. So just to explain further, time of travel, it basically depends upon the uppermost. So that means the overall area. Time of travel means from all the regions when it comes, what is the time which is required. So from the uppermost or from the maximum farthermost point, uppermost inlet up to the point of concentration. That is the point which we are considering. That is time of travel. But time of concentration, basically, it says that from the most remote point across the ground surface, time of concentration is the time required by the runoff from the most remote point of the catchment to reach the point of concentration. So, uppermost. Okay, sorry, I explained it wrong. I'm talking about time of concentration. That is this figure. And the time of travel is, we have learned the other figure. That is, you have an inlet point. So from that inlet, so if this is your initial inlet point, from this initial inlet point to reach the next point, that is, the time required for traveling to the uppermost inlet up to the point of concentration, the region which we are considering. So that is the time of travel. Sorry, I while saying my bad, while saying I made that mistake. So this is correct. That is the time of travel is the time required by the storm traveling in the uppermost inlet up to the point of concentration. And time of concentration is, time of concentration is this one. This we have kind of discussed in our previous tutorial also. And partial area effect also, it is that at certain, the peak flow can be when the upstream is not even contributing. That can even exist. This also we discussed in the last tutorial, so I'm not going deep into this. So let's proceed further. Question 10. The right order of modeling in SWMM is. So this is actually directly from the lecture. Anybody wants to attempt this?
The first is analysis is done, so I think E would be the first one.
First analysis is done. Okay. But before analyzing, you need to do certain things, right? How can you, like, the whole software we're using is to analyze and design, right? So
Default options and object properties are set.
exactly. First one is we need to set the default options in properties. Then second one,
Catchment and sewerage network and component are drawn for the study area.
correct. Then after that, so after we set the properties, we set the properties, then we divide. That is what is a catchment, then how is the sewerage network going, competence, yes,
Yeah.
correct. Then the
And then
third,
accordingly, then based on that, we again redefine the properties of object as per existing or proposed design.
correct, exactly. And then what would be the next one?
Then comes the analysis part.
Yeah, then comes our analysis part. And yeah, then
Analysis, then simulations, then results.
simulations and then results. Correct, Anurag. Very good. Yeah. So this is the exact process that we are following. And yeah, this is what we discussed in our lecture also. That is the correct order is given in the lectures. Okay. So let's go to the next question. Choose the correct statements from the following. The saturation near point of concentration influences the runoff more than areas farther away. Longer periods of light rain corresponds to lower runoff coefficient, and rational formula is the most popular method to determine stormwater runoff. So there is, yeah, choose the correct options, like which of the options are correct. Any guesses?
B is correct. Let me see with A, C,
Okay,
A,
B
and
is correct. Longer periods of light rain corresponds to lower runoff coefficient. Why? Why does this happen?
yeah, because if the rainfall is for longer time, the intensity of rainfall is low, and percolation will be more, like infiltration or percolation. 1 second, excuse me.
Okay. Okay, okay, let Supriya come back. We'll have a discussion on this once more. Uh, yeah,
C
so
is correct.
she's correct. So she says
C,
that
C, 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 C,
C
C.
is correct. Okay, C is correct.
Oh.
Rational formula is the most popular. Yes, that we have discussed. It is the most popular method to determine. C is correct. What about A, Anurag? Saturation near point. Yeah. Anybody? A, is it right or wrong?
A is also right.
A is also right. And okay, A is, why is A right? Like, why does only the near point influence more?
Travel time is less, no?
Yeah, travel time is less. It not just travel time is less is the main reason, but along with that, basically, if it is a farther area which has got what okay, actually it
More.
relates to this option B also. Yeah. So if it is already saturated, then the runoff will be higher. Like you will have more runoff which is coming because it is already saturated. Percolation reduces, so more will come. So when the region near the point of concentration is saturated, it immediately comes into the catchment. But when it is a farther region which is saturated, while coming, if there's another region which is not saturated, then percolation will happen and water will be lost over there. Stormwater will be lost over there. So that brings us to our option B. So Supriya said that is right, but is there any difference in opinion? Do all of you feel that option B is also right? Okay, so actually option B is wrong. The thing is, longer periods of light rain corresponds to lower runoff coefficient is what is given. It should be higher runoff coefficient because her reasoning was in fact right. Like when it's saturated, percolation after a point, the percolation reduces. So when percolation reduces, more runoff happens because it's already saturated. So from that point, there's more water which is running off. So our runoff coefficient that we are giving, it actually increases. So option B is the wrong answer over here. So our answer is A and C. Has Supriya come back? Okay.
Yes, I am back, and now I understood because it is actually asking the coefficient. I didn't read the
Yes,
lines
yes, yes. We were talking
correctly.
about, okay, it is a runoff coefficient which they have asked. Right. So it will be higher and not
Yeah, I
lower.
was talking. Yeah, right.
Yeah, sure. Yeah, so the same reason why is option A correct also. Like it's the same reason which was already explained. So yeah, so in the
Yeah.
lecture, yeah, in the lecture also, this is, sorry. Yeah, in the lecture also, this is what we had discussed. So yeah, so this is that option B. Longer periods of light rain saturates the soil, so which means it has a higher runoff coefficient. Okay. So yeah, so this is the other point. Saturation near point of concentration influences runoff more than areas farther away. So these were the two options we have. So now we are almost like only 5 minutes left. So I will just quickly jump on to one more numerical which was there because I think theory questions can be easily solved. So I'm just, yeah, so this is that numerical. So let's just jump on to that. And if the other theory questions are actually very easy only, so it can be solved. So let's jump on to this one. So determine the minimum required diameter of a circular sewer making use of the following data. So we have the area, population, uh, maximum permissible velocity. Okay, all this is given. So we are basically asking diameter of a circular sewer. So mainly we have been asked to design a combined sewer. I'm sorry, the wordings might it's missing over here. So we are asked to design the combined sewer. So for combined sewer design, how do we go about it? What are the components that we need to consider for combined sewer design? Yes, Supriya.
Yes. I didn't listen. Can you please come
Yeah, so
again?
no, I was asking what are the components that we need to consider in combined sewer? Like what will be there in a combined sewer?
Combined sewer will have stormwater and sewerage both.
Yeah, so stormwater plus sewerage both will be there. So
Yeah.
we'll have to see what is the quantity of both stormwater and sewerage. Like usually first we take sewerage and then we calculate stormwater what is required and we add it up and then we get the overall quantity or the based on then based on the quantity we go for the area or the diameter of the pipe which is required. So let's get started. So first one, in order to find the sewerage which will be generated, let's say what will be the so from the data we know what is the quantity of water which is being supplied, right? So we're going by that. So what is the quantity of water supplied? What all do we have information over here? We have the population and we have the rate of water supply in liters per capita per day. So the overall water which will be quantity of water will be, so basically it is population into the rate of supply. I'm just writing it as yeah, rate of supply. So that is over here 50,000, right? 50,000, no? Yeah, 50,000 into 230. So this will be so. But again, if you go to the this one, it is liters per capita per day. So it's per capita per day. So this per day we are converting it into seconds also because this is what we did in our water supply calculations. It's the same continuation of that. So this divided by 24 into 60 into 60, so which will give us liters per second. So what does that work out to?
It is 133.1019.
Yeah, so I'm just rounding it off to 1 liters per second. Right. Cool. So so this is the for the average. Now maximum or the peak discharge, we have learned that we are assuming it as 1.5 times the actual. So maximum uh, discharge is 1.5 into 133.1 liters per second. So that works out to,
199.65.
yeah, 199.65 liters per second. Correct. So now we need to find what is the sewage which is generated. So usually we can assume like about 75 to 80 percentage of this is generated as sewage. Like whatever we supply, 75 to 80 percentage will be. But here there's a small catch that is in this question. It is not mentioned that you need to assume anything. So since it's not mentioned, like no assumptions are mentioned, we are assuming 100% or we are basically over designing for the peak load, which in practical terms or in actual, when we are practically employing this in an industry, we might not do it. But then for the question's sake, or basically we're following the gate usual pattern. So when nothing is mentioned in the question, we are assuming to be the maximum or the peak flow which is there. So we are taking 100%. So that is one assumption that we are doing in this question. You might need to make a note that in your assignment question also you'll have to take this assumption. So we are taking assuming that 100% of 100% is generated as sewage. Whatever we are giving, 100% is generated as sewage. So we're making this small assumption over here. So this is one important assumption also. Fine. So based on this, we have got our sewage, how much will be generated. Now, in the second one, we need to, so now we are going for stormwater. Yeah, so stormwater calculation, we need to find the quantity. So, three things we need. So first, for stormwater, so we have the time of entry 5 minutes and then time of flow 20 minutes is given. So based on this at TC, that is time of concentration, we have learned that time of concentration is basically time of entry, that is how much time it entry plus time of flow also, that is to come to the mouth of the catchment, mouth of the pipe, and the time to flow also, like that, to the point of concentration which we need. So yeah, so that is 5 plus 20, which is 25 minutes. So let that be over there. And we also need to find I, which is the intensity. So if intensity was, if we had an IDF curve, then we could have easily found the intensity. But since IDF curve is not given, we have to use the empirical formula. So last time we used this empirical formula in the last tutorial also, which is basically 25.4 into A divided by T plus B. So this is the formula. So in this A and B, if you remember, we base it based on the time, like the time of concentration. So that is the reason why we found this time of concentration before finding the intensity. It is to find intensity only, but in this formula to find A and B, it is dependent. That is A is equal to 30 and B is equal to 10 when the time of concentration is 5 to 20 minutes, and B is equal to 40 and A is equal to 40 and B is equal to 20 when the concentration is 20 to 100 minutes. So this is there in our as a standard. So this also we need to remember, like these are certain things which is not given in the question, but we need to remember in order to use this one. So for here, since it's 25 minutes, we will go with A equal to 40 and B equal to 20. So let's come back and find what is the intensity. 25.4 into 40, which is our A, and 25 plus 20, which is our B. So what does this work out to?
$45.
Can you just check that on screen? I'll also check, maybe I also made a mistake.
22.5, correct.
Correct. Okay. Yeah. So it is 22.5. So that is intensity. So once we get, so basically we have found, we are interested to find Q. So once we get intensity, what is the formula to find Q? Any guesses? Okay, CIA. That is coefficient of runoff, intensity and area into area. And so this one again, we get, yeah. So we're using a factor also 360, like in the lecture, it's basically when we're converting meter per second liters, like all that, we're getting this factor. So in our lectures also, we are mainly following the CIA by 360 because our final answer we are which unit are we? Yeah, quantity in meter cube per second is the quantity that we're given. So we have this this one by divided by 360. So yes, so C. So let's see what is C. Do we have C in the question? Let's go back to the question. So basically the permeability factor is given over here, which is 0.45, which is our C value over here, which we will be considering. So our 0.45 into intensity, which is I, which we just found from here. So I'm just replacing it into A. What is the area? So let's go back to the question. Is area given? Yeah. So the area to be served is given as 120 hectares. And we also know that the unit which we need to use in the CIA formula, it should be in hectares itself. So we don't have to do any conversions over here. So into 120. So how much does, yeah, and obviously the factor 360, almost forgot, yeah. So how much that work out to? Right. So if this is there, then what will be the combined quantity which is there? Combined Q would be, we are adding it up, 0.91997 plus 3.386. So which is equal to 3.5865. So this is Q. So once we have Q, basically we are interested to find D, right? So Q is equal to AV, the same thing. And A, we know that it is pi D squared by 4 into V. So from this, we will find what is D. So I'll just initiate it. So basically, our, yeah, so let me just go pi D squared by 4 is equal to, so A is equal to Q by V divided by, yeah, so here V is given. So what is V? We didn't calculate V, right? But we don't have to calculate here. V is given in the question. That is, the maximum permissible velocity is 3.4, which is given in the question. So which means, yeah, so maximum permissible velocity is given. So when we design also, we need to consider that. So our V from the question, it is 3.4. So let's put that here. So denominator V, which is 3.4. Right. So this one would be pi, yeah, I'm just, okay, so D is equal to root of, okay, I'm not doing this calculation, but I'll just write it out over there. D is equal to. Okay. Was anybody able to solve this?
0.579.
D is 0.579.
Hmm.
Okay. No, that's not the answer. So basically, let's go, what does D square by 4 come up to? Were you able to get this answer for D square by pi D square by?
1.33.
You got 1.33. Okay, I am getting it as 1.05.
1.15. D is 1.15.
Yeah, D is 1.15. Exactly, correct. D is 1.15. So we've been asked to find the diameter, right? So usually, yeah, so 1.15 we can round it off, right? And then
1.2.
yeah, so 1.2. So 1.2 would be the diameter that we would be choosing. So let's see. Yeah, so options also we have 1.2 over here. So option A, D is equal to 1.2. Okay. So yeah, so this was, I don't think I have any other numericals. Yeah, so these were the 16 questions, like, which is there. It's not the other questions are not very difficult. It's just like, for instance, this question number 16 is just direct definition, which is there from the presentation only. So I don't think I need to go through them. The other regarding effective range, yeah, this is also a very easy question. It's just direct definition of time area method, which is there, question number 15 also. So I'm not going into them because we have run out of time. If you have any doubt, you can ask, or if you want me to go through the questions, I can go through.
Madam, one inquiry. Initial first 4 assignment, I have missed the assignment because of the late enrollment or something. So,
Okay.
and right now I can solve only 8 assignments.
Okay.
So that is okay.
Actually, I'm not the person to answer that. NPTEL team should be able to answer that. So maybe you can put it in the discussion forum. Somebody from the main team, like who manages the marking and assignments and all that, they will come and answer. So I don't know about this.
Okay, okay, because they have mentioned that best of the 8 assignments they are considering. So
Yes.
anyhow, if we are attempting 12 assignments, only 8 will be considered.
Is it so? Okay, okay. It's best of 8. Fine.
Yeah, only out of 12, only 8 assignments will be considered.
Okay, okay.
This
Fine.
is, I'm sure, because for transportation planning part, I missed one of the assignment. So I had a query for this. Then they replied that out of 12, only 8 will be considered. So no problem.
Okay, so then that's good. Yeah, I was not aware of this. Thanks.
But first 4 are easy. Now it is more
Yeah,
to the
that is.
calculation. Yes,
But
yes.
I can also tell you that the last four are last four nahi, but assignment 11 and 12 is comparatively easy.
Fine.
Okay, okay, no problem. It's good now.
Yes, actually, it's not just that. No, for the final exam also, these questions will come. So it's good if you're solving these questions in these assignments. Uh, I believe that three of you have registered for the exam, right?
Yes,
Yes,
yes.
I have registered.
Yes, so it will be useful, especially the calculation part. It'll be very useful. Okay.
Thank you.
I have one thing for transportation planning part. If you could convey, actually, 3 numericals I'm not able to solve for this week assessment. I'm putting for in the query forum, but I got the reply, but I couldn't understand the reply also. And then I replied back, give me some similar type of solution so that it would be easy for me to understand. But tomorrow is the last date, so if you can help me with this, if someone from,
Yeah,
if you
yeah.
know the
Yes,
team,
yes. I'll talk to Niyata. Niyata is doing this one, right? Or the live sessions for you.
yeah, I think her.
Yeah, it is Niyata. So yeah, so I will talk to her. But yeah, tomorrow is your submission, right? Okay, I'll let her know.
If by tomorrow morning or afternoon maximum she get me some similar type of solution, then it would help me to solve the assignments question.
Okay, sure. Noted.
Yeah.
And madam, yesterday's live session was covering the same
Same thing,
same
same
to-
thing. Yeah,
same thing. No?
same thing. Yeah. But if you want to see, recordings are available. There in NPTEL, the last portion recordings will be there. Where both today's and yesterday's recording both will be there. So you can go through that also. It's basically the same questions. Solution method is also more or less same. Some explanations are probably maybe some additions are there here. Some are there here in mine. Some are there in previous. But the essential idea is we solve the same questions. They're just previous year's assignments. So now there were 16 questions in the previous assignment, but I could like with time constraint we didn't go through all the 16, right? So maybe the other questions are solved there. I'm not sure about it. So, but it's usually the same, repeat only.
It's almost repeated. I actually I attend that also.
Okay, okay. Great, yeah. So it is the repeat. Most of the days it eventually becomes a repeat. As I said, the idea why 2 sessions was there for this course was because there were many people, many students who had enrolled. Though not a lot of people are coming for the live sessions, but a lot had enrolled. Even for exam, a lot have enrolled actually.
No, it helps actually the live session. I can tell you, if due to some small confusion, we give the wrong answer, and if we discuss, then it comes very clear.
True, true. Very true, very true.
Be it numerical or the theory part.
And one thing, madam, for examination, we need to go through the CPHEEO, this specification.
So, most of the content from CPHEO, whatever is required, I think in
It's covered.
lectures also we have given as tables and all that.
Yes, yes, yes.
So, yeah, so I wouldn't say you need to learn the whole thing, but you can know that content if you know it's good. But again, you don't have to memorize anything because when
Yes,
it comes
yes.
to problems and all these, like for instance, today we had to look into a table. So that values will be given usually. That assume this value or a table will be given, and from that table we can take. So you need not memorize anything, but certain factors like design period of a pump, design period of
Yes, yes.
and water requirement, that is for hostels how much is the water requirement which is there. So those are again given in the manual only. So that certain things like practical things, it's good to remember also. I wouldn't suggest to learn anything which was not discussed in the lectures. Like whatever was discussed in the lectures will only be there.
But this is a government specification related to the designing.
Yes, yes, it is important. I'm not saying it is not important. I'm saying that for the exam point of view, which is not discussed, if you don't remember, like the thing is, we wouldn't expect you to remember that. But it is a very valuable document, and if you look at most of our content is also taken from that. Like in most of the lectures in the references, you will find the
Yes.
the manual also. So yes, so
So
it
what
is
I'm
important. If you can go
what
through
I'm
and learn it, then it is the
yes,
best
yes.
part. Like it is very good. It will be useful not just for the examination point of view, but for the practical application point of view will also be useful. But considering that there are already what 60 presentations and content to learn,
Yes, yes.
it might be difficult. That's it.
No, no. What I'm asking that for the designing purpose or designing anything related to this sewage and the storm water, this manual is considered. Na this
Yes,
manual is
yes,
a guideline na for India.
yes, yes. It is a guideline.
Ah,
Yes,
and even the softwares what you have suggested, two software, those
yes.
are also related to this manual.
It is related to this manual, yes. And all the, as I said, all these standards which we are discussing here, again, we are taken it from the manual only.
Okay, okay, good. Thank you very much.
Yeah, okay.
Good night.
Okay, fine. Thank you all.
Thank you.
Yeah, see
Good
you all
night.
next week. Yeah, good night. Bye bye.
Good night.